And now a quick look at question 3. This is a bit tricky. It's down as one of these sort of higher level ones, and it's a bit tricky because they're doing something to you which you may not always get asked about. Right, first of all, straightforward enough, a ball dropping and then rebounding to less than its original height. So sort of, if you think about it, this is like a ball and you drop it, it hits the ground and it comes back to maybe not quite as high as it was before. So there's your ball doing that. Then they ask you to do some graphs of what the motion of the ball is, its velocity. Now, the thing you've got to remember is this is free falling, and then it's bouncing, and you've got an acceleration due to gravity. Now, because this has sort of got plus and minus vectors, I quite fancy saying that we should say that in this case g is minus 9.81 meters per second squared, and we'll define upwards vectors as plus and downward vectors as minus. That way, we can get a bit of sense out of this. So let's think, what is this ball going to be doing when we first let go of it? Well, it's going to be travelling downwards. It will start at 0 velocity, and it will travel downwards, and it will accelerate. It'll be under constant acceleration, because it's just a constant accelerating force due to its own weight, so it'll accelerate downwards at a steady rate. Now, when it hits the ground, it's going to instantaneously, pretty much, start going upwards instead. So I will then do this as sort of an instant change to an upwards velocity, and I'll just leave that there for a second while we think about it. And if you like, we could draw a little dotted line in between these two, just to show that we're aware of the fact that it was still doing stuff, but we couldn't easily see it. So there's the ball, hits the ground, bounces vertically. Now, if I wanted to be cute about this, I could say, well, it's not quite going to go up as far as before, so maybe this shouldn't be starting off quite as high as the original velocity, so I'll just pull that down a little bit. The crucial bit that they want you to spot, though, is that this second bit of velocity is going to be decreasing at the same rate as the first one. So I'll sketch this one parallel, but notice now we've gone velocity vertical, this section of the graph, but decreasing as it gets slower and slower, going up in the air. Here it was falling, getting faster and faster, bounced, instantaneously going upwards at high velocity, but then gradually slowing down. And so there we go with that graph. Now, the second bit of this, I don't entirely agree with the marking scheme. I know you hate me saying that, but I don't entirely agree with the marking scheme, because they've said, right, plot a graph of the acceleration of the ball against time. I'm thinking, okay, well, first bit of the graph, it's slowing down, its acceleration slowing down is your usual minus 9.81. So let's just say to ourselves, right, minus 9.81, and I'll just carry that on for the sake of it, just until it's sort of around about the same place as that little dotted line. And then it bounces, does this instantaneous change, and it's then moving upwards, but its velocity is decreasing. Its upwards velocity is decreasing, meaning its velocity is increasing in a downwards direction, or if you like, its acceleration is downwards, as its acceleration was downwards here. So, in fact, the second bit of your graph looks just the same. That's what they're after, is those two bits of the graph being the same. Now, you could argue, if you were being a bit precious about this, or a bit pedantic to use the correct term, you could say, well, hang on a sec, in that bit in between, it's suddenly got itself a very, very, very big positive acceleration as it changes direction. So I'm just inclined for my own peace of mind, to do a little sudden jump there and then carrying on. The example they've given just has those two bits at the bottom, but I don't know, I think that's a more complete answer. It's only 1 mark. In this first part, we've got 4 marks for getting that, for getting instantaneous change, and they also want you to have these at the same slope, meaning it's the same rate of acceleration. Right, second bit, this is where it gets a bit nasty, because they've said, right, we're not sending a projectile horizontal, we're sending a projectile at an angle. Now, you can work all this out, it's not actually that difficult, but what they're expecting you to do here is just realise what's going on. So, acceleration vectors, not the velocity, the acceleration. So, you throw the ball at an angle to the horizontal, it follows this trajectory, and I think we're not worrying about any air resistance. Don't worry about the bouncing, we've done all that. This is just being thrown up in the air and the ball goes wee like this. Now, acceleration vector. The only acceleration that you've got to worry about is acceleration due to gravity. So, at P, the acceleration vector is there, and just in keeping with my original colour coding, I'll do that green. And guess what? The acceleration vector at Q, the only acceleration it's got is the same it had at P. It's exactly the same. Now, momentum. Momentum depends on the direction something is travelling in. So let's pick a momentum colour, which I don't know, I've always felt momentum is purple. Let's do a momentum vector, the direction it's travelling in. So here you go, P. We can do a momentum vector at a tangent to the movement there, so that's momentum, and that there is acceleration, and that's acceleration as well. And in this next one, the momentum vector is going to be at a different angle. Now, the only thing I'd quite like to do here is if I clone it, it's no longer pointing that way, it's now pointing horizontal. And if you, I mean, they've only asked you to show the direction, but if you want to be a bit cute, that will actually be travelling a little bit slower, because it will have slowed down a little bit between there and there. But the crucial thing is that the direction there is parallel to the movement. So those arrows showing directions should get you your 4 marks for that question. I don't really think that's too difficult. Now, here's where it gets ever so slightly exciting. Now they're after the momentum of the ball at the moment it's been launched. They've told you on the diagram that it's heading off upwards at a 50-degree angle to the horizontal. It's travelling at a speed of 15 meters per second. So that there is 15 meters per second at that angle. They want you to work out what is the magnitude of momentum when it's at Q. Now, this is where you've got to think a bit, right? This ball has been projected at 15 meters per second. It's going to have a horizontal velocity vector, and it's going to have a vertical velocity vector, right? And it'll have ever so slightly larger vertical velocity vector as that angle's more than 45 degrees. Now, they're asking you what its momentum is at Q. Now, at Q, it's just about to start coming down, having gone up. So, at Q, you've got velocity vertical is 0. And you've got velocity horizontal is just the horizontal component of the velocity. So we don't need, all we need to know is what part of that 15 meters per second at 50 degrees is the horizontal component. And okay, my lazy way, you're closing the angle, that's actually going to be 15 multiplied by the cosine of 50 degrees. You can work it out as a triangle if you like, because looking at the diagram, if you've got that as your vertical component and you've got that as your horizontal component, or if you prefer, put that one there. Then angle between those two is, angle between those two, well, that angle there is 50 degrees. Alrighty. So you want the amount of that vertical component. You know that that is 15. There's 50 degrees. The cosine of 50 is the the cosine of 50 is opposite over hypotenuse. The sine is opposite over hypotenuse. The cosine of 50 is adjacent over hypotenuse, and that adjacent is your horizontal component of the velocity, which is what we want to find out. So there's our horizontal component. So 15 cosine of 50 is going to give us our horizontal component. So we'll say down here, and then V horizontal is 15 multiplied by the cosine of 50 degrees, which, if you plug that into your calculator, gets you 9.642 meters per second. Right, and momentum is going to be mass multiplied by velocity. So it's going to be 0.15 kgs multiplied by the 9.642 we had before. And that gets us all of 1.446 kilogram meters per second, right? Which we can do our usual rounding to 2 sig figs here. Call it maybe 1.4. If we do this thing of sort of ignoring the 1, it could be 1.4 or maybe 1.45. And always remember, you can actually quote momentum in units of Newton seconds as well, because that's absolutely the same, because it's force multiplied by time a force is applying for. And there you go, with all of your answers complete. Yeah, marking scheme wants you to come up with the 1.45. Usually if it's 1 point something, generally, if you even have 2 sig figs, do it as 1 point and then 2 sig figs there. Right, there you go. Those are all correct. Hope that's helped.